Alright, so let's look at a small example. So 2 by 2, x1 prime is 4x1 minus 3x2, and x2 prime is 6x1 minus 7x2. So this is two equations. These are the functions we're looking for. And the 4, negative 3, 6, negative 7 are the coefficient matrix. So it can be written as x1 prime, x2 prime equals to x1, x2 with the coefficient matrix before that. So it's 4, negative 3, 6, negative 7. And this is homogeneous because there's no constant term. So I'm going to write it as a vector x prime, let's say of t, equals to 4, negative 3, 6, negative 7 times x. Okay, so we're not going to learn how to solve this in this section. We're gonna learn how to solve this in section 7.3. Right now, we're gonna check if something is the solution. So we're gonna check that x1 vector equal to 3e to the 2t, 2e to the 2t, and x2 is e to the negative 5t, 3 times e to the negative 5t are solutions. Okay, so to check their solutions, what we do is just plug it into the equation and see if it fits. So let's do that. So let's check the first one. So this is x1, then x1 prime is equal to 6 e to the 2t and 4 e to the 2t. So that's the left-hand side. And the right-hand side is 4, negative 3, 6, negative 7 times x, which is 3 e to the 2t, 2 e to the 2t. This is equal to, so e to the 2t stays there. 12 minus 6 is 6. 18 minus 14 is 4. So it looks like the left-hand side equal to the right-hand side. So this checks out. And we'll do the same thing for x2. So x2 prime is minus 5 e to the negative 5t, negative 15 e to the negative 5t. And the matrix times this vector equal to, let's do this again, 4 minus 9 is negative 5, and 6 minus 21 is 15, and the rest is the same. So it checks out. So these two are indeed solutions. So before we're gonna write down a general solution, we need to check if they're independent. So to check they're linearly independent, we'll check the Wronskian. So the Wronskian of these two vectors is the determinant of these two vectors lined up. So it's 3e to the 2t, 2e to the 2t, e to the negative 5t, and 3e to the negative 5t. This is not hard to calculate. This is equal to 9 times e to the negative 3t minus 2 times e to the negative 3t, which is equal to 7 times e to the negative 3t. Regardless, 7 is not 0, e to the negative 3t is not 0, so this is never 0. So x1 and x2 vectors are linearly independent. Okay, so this is a system of two equations. We have two linearly independent solutions. So the general solution is of the form x of t equals to x1 of t times c1 plus x2 of t times c2. If you don't like the form vectors, we can translate it into x1, x2, these are functions, equal to c1 times 3e to the 2t, 2e to the 2t, plus c2 times e to the 5t, negative 5t, 3e to the negative 5t. Or you can write it in terms of two individual solutions. So the first solution, the solution for x1 is x1 equal to c1, 3c1 e to the 2t plus c2 e to the negative 5t. And x2 is 2c1 e to the 2t plus 3c2 e to the negative 5t. Let's move down here a little bit. So this is the general solution. Now suppose we want to solve a particular solution given initial condition. So let's suppose the initial condition is x1 of 0 equals to, let's say, 1, and x2 of 0 equals to negative 1. Why not? Then we get a system of two linear equations. So 1 equals to 3c1 plus c2, and negative 1 equals to 2c1 plus 3c2. Gonna quickly use Cramer's rule to calculate this. So c1 is, the denominator is 3, 1, 2, 3. Numerator is 1, negative 1, 1, 3. It's equal to 4 here, and 9 minus 2, 7. Okay, and c2 is same denominator, but different numerator. 1, negative 1, so denominator is still 7. Numerator is negative 5. Okay, so this is C1 and C2. So the solution, so the particular solution is x1 equals to 3c1, that's 12 over 7 e to the 2t, minus 5/7 e to the negative 5t, and x2 is 2c1, that's 8/7 to 2t, plus 3c2, so that's 15 over 7 e to the negative 5t. All right.